This is the solution to problem 1 from the 2019 AP Physics C Electricity and Magnetism free response questions. And let's slide down a little bit here to see what the first one is. They're giving us a diagram of what's going on, and they describe this. A very long, thin, non-conducting cylinder of length L is centered on the y-axis as shown above. The cylinder has a uniform linear charge density plus lambda. Point P is located on the y-axis at y is equal to c, where L is much greater than c. So they're asking us to the first question here, on the figure shown below, draw an arrow to indicate the direction of the electric field at point P due to the long cylinder. Okay, and we can see this down here. This is just like a little graph, but let's take a look at how we're going to figure this out. So to find the electric field is force per unit charge. So we need to consider the displacement between some differential charge at any point along that non-conducting length on the cylinder and the point of measurement. And there's a continuous differential charge along the cylinder, and they've described that as lambda is equal to dq dl, or dx in this case. So we can rearrange this a little bit and we get dq is equal to lambda dx. So for any infinitesimal length on this, we'll have some dq that exists here, and this creates a field at point P that points off in this direction, and this is some dE that's associated with that. And we have to consider how this changes as this position varies along. So we have to take a look at maybe another example point here that's going to produce something in this direction that's coming up here to create another dE based on some dQ over here. This part of the problem doesn't ask us to find the magnitude of the E field, only the direction. And what we notice is that point P is placed midway between the endpoints of the non-conducting cylinder. For every position to the left of the point that generates some dE, and that would be on this side, we wind up getting some dE that points up and to the right. So it's off in this direction here. And for every one of those points to the left, there is an equally distant position to the right of the point that generates an equal magnitude dE that points up and to the left. So everything, this is symmetrically here, and we take advantage of this symmetry to simplify the math. So when we integrate, in fact, we'll write this down here. When we integrate this out up here, over the length of the cylinder, the horizontal components of the E field will cancel at the midpoint. The resulting E at point P radially points away from the cylinder. So everything pointing to the right and to the left cancels out, and what we're left with is something that just points up. So we can fill that in on the chart they give us below, and it says that the arrow should start on and point away from the dot. So what we have here is something like that. Let's slide down a bit to the second part of part A. And they're asking us to describe the shape and location of a Gaussian surface that can be used to determine the electric field at point P due to the long cylinder. And we're going to have to take a look at what we can use here and where we're going to place this. And they want us to describe this. And we can take a look at this. The purpose of selecting a particular Gaussian surface is to simplify the relationship between the field direction and the surface direction. And finding a surface that is either perpendicular to the field at points on the surface or parallel to the field at points on the surface simplifies the math that's associated with the dot product, right? Because we will actually take a look at what Gauss's law is here, and we know that E dot dA is equal to the enclosed charge divided by epsilon naught. So for a cylindrical object with a uniform charge density, selecting a cylindrical Gaussian surface achieves that purpose. Note that the length of the charged object is finite, right? We've got this thing here, it ends here. Now it's, we take advantage of the fact that L is much greater than C here to make some approximations. So we need to make the length of the Gaussian surface cylinder much shorter than the length of the charged object. And this is because the horizontal component of the electric field only cancels out completely at the midpoint. As soon as you start moving away from the midpoint, the field produced by the charge to the right of any particular point is going to be greater than what's produced by the left side, so you do get some residual field that's going on there as you move to either side. But we can minimize the electric flux passing through the circular ends of that cylinder relative to the electric flux passing through the lateral surface area of the Gaussian surface by bringing those circular ends close to the midpoint. And so we're going to actually slide this down a little bit here so that we can see this. Describe the shape and location. So what we're going to do here is we'll create a cylindrical Gaussian surface, and there's what we're going to do here is we're going to make the radius of this cylindrical surface equal to the distance of the measurement point from the charged object. So point P is going to be placed on the Gaussian surface, and that allows us to calculate the E field exactly at that point. So if we're going to describe the shape and location, it starts at some, and if we give this a length D, so this is going to go from minus D over 2 to plus D over 2. And the radius of this particular cylinder is C, and it is centered around the x-axis. For part 3 of part A, they're asking us to use your Gaussian surface to derive an expression for the magnitude of the electric field at point P, and to express the answer in terms of lambda, which is the linear charge density, C, which is the radius or the distance from the point, L, which is the length of the charged cylinder, and any physical constants. So we've already set it up, and we know that we've got a cylinder here. And once again, we'll write down, we'll write down Gauss's law, where we get E dot dA is equal to Q enclosed divided by epsilon naught. And we know the field is perpendicular to the lateral surface area of the cylinder, and based on our approximation by making this cylinder very short compared to the length, that we can ignore the electric flux through the circular ends. So the area that we're going to have here that we're concerned with is going to be pi, that's going to be 2 pi c d, where d is the length of the cylinder, or the length of the cylindrical Gaussian surface. And c is the radius of the Gaussian surface. So we can simplify this because E is perpendicular to the vector area. So what we have here is E times A is equal to Q enclosed over E0. And now what we need is to figure out how much charge is enclosed in that. But we do know that, as we said before, lambda is equal to dq dx. So dq is equal to lambda dx. And we know that we're going to integrate this. So what we're going to get is dq is going to be equal to from minus d over 2 to plus d over 2 lambda dx. And when we just do this out, we get lambda x evaluated from plus d over 2 to minus d over 2, and we get lambda d. So our total enclosed charge within our Gaussian surface is going to be lambda d, and we know that A is equal to this from before, so what we have is E, E is now going to be equal to lambda d divided by epsilon naught, and we're going to move the A over, so the field is going to be lambda d divided by 2 pi c d epsilon naught, and the d's cancel out, and what we're left with is that the magnitude of the electric field at point P is going to be equal to lambda divided by 2 pi c epsilon naught. For part B of problem number 1, they're telling us that a proton is released from rest at point P, and on the axes below, sketch the velocity v as a function of position y and acceleration a as a function of position for the proton. And they're giving us a couple of graphs here. So we need to sketch velocity and acceleration of a proton as a function of position. We don't need to derive any equations, so we can use the existing information from the problem so far to approximate the graphs. And what we're going to start with is that we have some E, and we know that that is a function of R, that we just calculated that out, and that this is lambda divided by 2 pi epsilon naught R. Now we calculated that for one specific value, C, but really if you, when you extend that out to any length beyond, beyond the line, this becomes the electric field. We're just replacing the C with an R. And the proton starts at rest at point P, and we know that the direction of the force is going to be the same as the direction of the E field. So we know that that proton is going to move along a radial path away from the positively charged cylinder. And we'll sketch the acceleration first, and then we'll use that information to approximate velocity. So we know that if our field is lambda divided by 2 pi epsilon naught R, then what we can rewrite this as the magnitude of force is going to be Q times E, where Q is just the charge of the proton. And we also know that that's equal to ma. Force is equal to mass times acceleration. So we can rearrange this a little bit, and what we wind up getting is that A is equal to Q E divided by m, and that is going to end up equal to q times lambda divided by 2 pi epsilon naught m times r. So what we have here is that we know that it's at rest at point C, and this is our acceleration. So we have some initial force at some value that it starts out as, and in fact, we're not going to draw this down here, we'll draw this up here. So there's an initial value that's associated with that force that exists at r is equal to c, but we see that as r increases, or in this case y, because this is going to be along the y-axis, so why don't we rewrite that here, is equal to q lambda divided by 2 pi epsilon naught m times y. As y increases, the acceleration decreases, and this is going to actually look something like this. The acceleration starts at an initial max value and decreases. It never actually reaches zero. It moves asymptotically towards the zero axis as y gets larger and larger. So now that we've got this, we can approximate velocity based on the acceleration curve. So we'll start over here, and it starts at rest, so we know at point C that proton has zero velocity, but we also know that it accelerates, but as it moves further and further away, the acceleration decreases. So we start out with a steep rate of change, and it gets lower and lower, but because acceleration never actually goes to zero, this value just keeps on increasing as it moves away. It just increases at a much slower rate. So those are the two graphs, those are the two sketches for acceleration and velocity based on position. And this problem doesn't ask us for a quantitative description of velocity, but for those who want to see this justified more rigorously, you can click on the link shown here, and there'll be a supporting video that shows the math behind this, and the graphs actually agree with that. Okay, so on to part C. The original cylinder is now replaced with a much shorter, thin, non-conducting cylinder with the same uniform linear charge density, plus lambda, as shown in the figure below. The length of the cylinder to the right of the y-axis is a, and the length of the cylinder to the left of the x-axis is b, where a is less than b. And they're asking us, again here, to just draw an arrow to indicate the direction of the electric field at point P due to the shorter cylinder. So we use the same reasoning that we did earlier in this problem. And the charge to the left of point P creates a field pointing away from the cylinder and to the right. So you get everything over on this side of point P generates some field that points up and to the left, and that changes, of course, as you move along. And then the charge to the right of point P also creates a field pointing away from the cylinder and to the left. So points over here would actually cause some E field in this direction. But the charge to the left of point P is greater than the charge to the right of point P, so the horizontal field components no longer cancel. There's a net horizontal component pointing to the right, along with the vertical component that's still pointing away from the charged cylinder. So we have something like this, but now we have this component and this upward component that's pointing along. So what we get is a net field that points up into, we get a net field that points up and to the right. So we will draw something like this in there. Finally, for part D, they're asking us, is there a single Gaussian surface that can be used with Gauss's law to derive an expression for the electric field at point P? And that's in this modified case where P kind of points up like this. And the answer to that is no. And they're asking us to justify this. And if we look back up at this diagram over here, just the way we talked about, the charge distribution isn't symmetric relative to point P anymore, the measurement point. And so the field isn't uniform over any complete surface, right? Everything is on a much shorter scale here now, and we can't come up with some type of cylindrical or spherical or prism surface such that the field is going to be uniform and consistent. So and that's due to the relative distance of the radius and the length of the charged object. So that's the reasoning why you cannot find some Gaussian surface. The field just isn't going to allow you to pick something. And that concludes, maybe there's one more. Oh, there is one more part. And then finally part E. Let's see. Once again, we're looking at this, this non-symmetric case, and a student in class argues that using the integral shown below might be a useful approach for determining the electric field at point P. And this is just the general equation for electric field, right, over a distributed charge. So this initial integral is actually, this is workable. We can keep that. And the student uses this approach and writes the following two integrals for the magnitude of the horizontal and vertical components of the electric field at point P. And we get these two expressions here. And what they ask us, once again, what of the two expressions above is not correct? Which expression is not correct? And to find what needs to be fixed here, or actually we can take the easy route on this. The fastest way to identify the incorrect component in this problem is to check the integration variable. Now, the charge is distributed along the x direction. And so we see that the horizontal component here has this dx that's here, but the vertical component has some dy, and this just doesn't make sense. We're not integrating over y, we're integrating over x. So that tells us that the vertical component is wrong just right off the bat. We don't need to get into a whole lot. But now they're asking us to identify two mistakes in the incorrect expression and explain how to correct the mistakes. So to find what needs to be fixed, let's take a look at how the components of the field are derived. That becomes the easiest way to find the mistakes and say what it is that we're going to correct. So what we can start out with is we know that E is equal to the integral of 1 over 4 pi epsilon naught r squared dq. And what we know is that r is the distance between any point along the x-axis, and that's c. So r squared is going to be equal to x squared plus c squared. That's just a Pythagorean theorem. And from earlier, we also know that lambda is equal to dq dx, which means that dq is equal to lambda dx. So we can swap out some variables and just replace things here, and we know that E in general, the magnitude of the electric field, is now going to be 1 over 4 pi epsilon naught x squared plus c squared. And we need to multiply that. We're going to replace the dq with lambda dx. And if we want to break this up into a horizontal component and a vertical component, we can take this field and we can decompose it into x and y components as we do any other vector. And we'll just draw a little triangle down here to indicate what's kind of going on there. And we know that we have some x value here, and we have some c value because this is our point P that they're giving us. And we know that the length of this is c squared plus x squared. But when we decompose, right, all we're doing is to find the x component, we're multiplying by the cosine of the angle, cosine of theta. And to find the vertical component, we're going to multiply by the sine of that. But the x component multiplies by x divided by c. So what we have here is E is equal to, or E sub x is going to be equal to lambda over 4 pi epsilon naught x squared plus c squared. Now we're going to multiply that by the cosine of this, which is just going to be times x. Oh, sorry, this is x squared plus c squared to the 1/2. And then we have times lambda dx. And what we get when we multiply this all out is what we saw up above. I'm just going to make some room here for this. So this turns out to be lambda, and I'm just going to bring the constants out in front of the integral, 4 pi epsilon naught times x over x squared plus c squared to the 3/2, because we add those exponents together, and then we have dx, and this becomes our x value for this, and hopefully I've got a little bit of extra room. You know what? I'm going to chop this out here. And just slide it down into the bottom just so that it's still there. And what we'll do is we'll do the same thing for e sub y, but now we need to use the sine component to plug that thing in, and what you get is this integral of lambda over 4 pi epsilon naught times x squared plus c squared. And now we're going to multiply it by the sine, but the sine of that from that triangle is going to be c over x squared plus c squared to the 1/2. And then we have our lambda dx in there again. And when we bring all of this together, we'll bring the constants up front. Lambda c over 4 pi epsilon naught times the integral of 1 over x squared plus c squared to the 3/2 dx. And if we take a look at our original expression for this, the actual question here was what to fix for the y component of this. So we have, let's just highlight this down here. This is our y component. And if we slide back up to see what the differences are, we can see that we can fix this by changing dy to dx. We can get rid of this y up on the top because we don't really need, I guess that's at point C. So this could change to c. And then we also need to change the exponent on the c squared plus x squared to c squared plus x squared to the 3/2. And those are three things that we can possibly do to make that y component correct. And it looks like that is it for problem 1. Stay tuned for a different video that goes into problem 2. Thanks for watching.